In this video, we're going to start to look at comparisons. How can we use comparisons to both other series as well as to integrals to determine whether a given infinite series converges? And to start off, we're going to think about the example of the series defined by an equals 1 over n. And I'll remind you that the terms in this sequence would be, well, if n starts with 1, we'll have 1, 1/2, 1/3, 1/4, and so on. Okay, so that's the terms in this sequence. And if we want to think about the series, then the terms would be, again, the sums of these. So 1 would be the first, the second partial sum would be 1 plus 1/2, and the third would be 1 plus 1/2 plus 1/3, and so on. Now, at a couple of points, we've started visualizing what the terms in a sequence look like. And one of the ways we've done that is by graphing the terms on the coordinate plane, where we have one axis to represent the index n and the other to represent an. And we're going to do something similar here. But let's think about, instead of n versus an, let's think about x versus f of x. And here, f of x, the function that we're going to be interested in is 1 over x. And notice that's going to match the values of the terms in the sequence when x is an integer. All right, and so let me label the integers here. 1, 2, 3, 4, 5, and so on. And what I want to do is I want to think about each of those individual terms in the sequence that we're ultimately going to be adding up as a little rectangle, where the area of the rectangle is given by the value of the term. So for our first term, the a1 is equal to 1. And so I could draw a rectangle that is 1 by 1. And notice if the height is 1 and the width is 1, then the area here would just be 1. And for the next rectangle, what I'm going to do is, starting at x equals 2, I'm going to draw a rectangle with area 1/2. Again, I'm going to keep the width at 1. So this distance right here is 1. But the height now is going to be 1/2. And I could continue the process. I won't label all of them. The next one will have a height of 1/3. The next one after that will have a height of 1/4, and then 1/5, and so on. All right, so each of those terms, each of those little rectangles represents a given term. And so we've got a rectangle for a1, we've got one for a2, for a3, and a4, and so on. And that means that the series, the sum of a1 plus a2 plus a3 on down the line, would just be the total area of all of the rectangles. Okay, so we can think about visualizing what an infinite series represents as the area under some curve, which is made up of the tops of all of these rectangles. And that's kind of convenient because we already know how to find areas under a curve. In fact, let me redraw this just a little bit bigger. All right, so I'm going to make my rectangles a little bit taller. So there's 1, there's 1/2, there's 1/3, there's 1/4, and on down the line. All right. The area under this curve would be rather tedious to calculate using an integral, because notice that would have to be defined as a piecewise function. But there is another curve, and I'll draw it in red here, that would be relatively easy to find the area under. And so if I were to draw the curve that connects all of these points, the claim is that we could actually find the area under the red curve with using an integral. All right, and how would that work? Well, notice this point has a y value of 1, since that's the top of my first rectangle. The next one has a y value of 1/2. So that's the point 2, 1/2. This is the point 1, 1. The next point would be 3, for the x value, and the y value would be 1/3. And in fact, this red curve is just y equals 1/x. So the curve that uses the function that we defined above, so there's the f of x used to calculate the terms in the sequence, gives us this red area. All right, so let me shade that really quickly. Area under the curve, right there. And I can easily compute the area under the red curve. That's got to be the integral from 1 to infinity of 1/x dx. And notice, well, that's a straightforward antiderivative. Antiderivative of 1/x is just the log of x. And so I would take that from 1 to infinity. And if we plug in those endpoints, we'll have log infinity minus 1. And really, we should be taking a limit here. But again, I'm using shorthand for when I plug in infinity. What I really mean is log of b as b goes to infinity. But notice that term wants to go to infinity. And so we would say this is a divergent integral. So the area under the red curve must be infinitely large. And if that is the case, then what do we know about the area under the rectangles? Well, based on our picture, there's all this extra area here. And so the area under the rectangles, which is, recall, that's the infinite series, the sum of 1/n from n equals 1 to infinity. Well, it's very clear geometrically that that must be greater than the area under the curve. And so since this is divergent, we can conclude that this sum must also diverge. All right? So, interesting idea there. If we want to say something about a series, one thing that we can do is we can represent the series as the area under a curve. We can find the area under another curve that can be easily computed with an integral, and then we can use the comparison, use the graph to compare the two. In this case, it was very clear that the series had much larger area than the integral, and so we concluded, basically, using the same notion that we introduced earlier in the semester, that if you are bigger than something big, then you must be big, right? If you're bigger than something divergent, then you must diverge. Okay? So that is the basis for one of the tests for convergence and divergence that we can apply to series in general. It's called the integral test. And before we get into the specifics of the test, let's look at one more example. Let's look at the sum of 1/n squared. And 1/n, we showed earlier that it diverged another way. And so this solution wasn't brand new to us, but I don't think we've actually looked at 1/n squared and proven its convergence or divergence. All right, so let's look at this sum right here from n equals 1 to infinity. All right, and so we're interested, an equals 1/n squared, and so we can define that as our function f of n. And we're going to try the same idea here. We're going to try to represent the series using area under a curve, the sum of a bunch of rectangles, and then we're going to compare that to some integral to try to answer our question. All right, so let's draw ourselves a picture here. Well, we'll first compute our first few terms. A1 would be 1/1 squared, so 1. A2 would be 1/2 squared, which is a fourth. A3 would be 1/3 squared, which is 1/9. And A4 would be 1/4 squared, 1/16. And so when we draw our picture, those are going to be the heights of our rectangles, and the widths of our rectangles will be just 1 as usual. Okay. So for our first rectangle, we'll draw a rectangle with height 1 and width 1. Our next rectangle with height will have height 1/4, and the one after that will have height 1/9, and then 1/16, and so on. And so notice that's representing A1, A2, A3, and A4. And we could continue that indefinitely. And if we wanted to find a function, we could draw a curve through here crosses the corners, the top left corners of each of those. And that red curve would be f of x equals 1 over x squared, right? Since this first point is 1, 1, the next point has x coordinate 2, but its height is the same as the first rectangle, or second rectangle, and we said that rectangle had height 1/4. And then this next one would be 3, 1/9, since it has the same y coordinate as the rectangle, and so on. All right? So, based on our picture, we can make a similar claim to the last example, that the area under the curve must be less than the sum from 1 to infinity. Read same sort of, it looks almost like the same picture. Obviously, the heights of the rectangles are a little different, but qualitatively, it looks very similar. All right, so let's actually evaluate that integral now. The integral from 1 to infinity of 1 over x squared. That's an example of that p integral that we studied earlier. And so we actually could just use our prior result, but just to remind ourselves, we'll take an antiderivative. So that's x to the minus 2. So antiderivative would be minus x to the negative 1 from 1 to infinity, which we could think of as minus 1 over x. It's another way of writing that, which would be minus 1 over infinity, minus, so plus 1 over 1. And notice 1 over infinity wants to go to 0 because the denominator is getting really big, and so we're left with just 1. And so what we can conclude from that is that 1 must be less than the sum from n equals 1 to infinity of 1 over n squared. Well, that's not all that helpful, because 1 over n squared could be convergent to a larger number than 1, and that would be true, or it could be divergent. It could go off to infinity, and that would still be true. So this is inconclusive in regards to the series. But not all hope is lost. So let me go back to this original picture here, and let's see if we can adjust our picture to help us. So what I'm going to do is I'm going to take each of those rectangles, and I'm going to leave off the first one, and then I'm going to just shift everything 1 unit to the right. All right? And so I'll do this in blue. All right, so here is A2. And notice now that rectangle is entirely below the curve, and it touches on the top right corner. And then on this next rectangle, I won't label it, but think of that as this black rectangle that was labeled A3, just shifted over 1 unit. And then the next one I'll shift over. And we could continue on down the line. And it's very clear from this picture that the blue rectangles, if you added up their area, it would have to be much less than the area under the curve, right? Because the blue rectangles are entirely below the curve. And what is the total blue area? Well, notice that includes all of the rectangles except for the first one. And so if we were to write down a formula for that area, it would be the sum from n equals 2 to infinity of 1 over n squared. Okay? So geometrically, we can make this argument that both of these inequalities have to hold. The integral has to be bigger than the sum if we start with 2, and smaller than the sum if we start with n equals 1. Okay? So, does that help us? Well, notice we weren't really interested in the sum starting with 2, but I think we can fix our argument just a little bit, because the sum from n equals 1 to infinity of 1 over n squared is just, well, it's 1 over 1, that's the first term, plus the sum from 2 to infinity of 1 over n squared. And if we know that this sum is less than the integral, then that must be less than or equal to 1 plus the integral from 1 to infinity of 1 over x squared dx. All right, well, we already know what that integral is. We evaluated that up above. We showed that that was equal to 1. And so 1 plus the sum from n equals 2 to infinity of 1 over n squared is less than or equal to, or less than 2. But remember, again, that was the sum from 1 to infinity. And so now we have two inequalities. We know that the sum of 1 over n squared is bigger than 1, but we also know that it's less than 2. So by comparing the sum to an integral, we've actually done two things. We've determined an upper bound, the sum is less than 2, and a lower bound, the sum is greater than 1. And if the sum is trapped in between 1 and 2, and the terms are actually all increasing here, so this is going to be a monotonic sequence. Well, if a sequence is monotonic and bounded, then we can conclude, based on our theorem we talked about a couple of days ago, that this must converge. The sum from 1 to infinity of 1 over n squared is convergent. And it's convergent to something between 1 and 2. All right, so this video was just to give you a sort of intuitive sense of what's going on behind the scenes when we use the integral test, but we'll make this formal and go through some examples of how we can apply this technique more generally in the next video.